All right, let me start the introduction. I think people are continue coming. It's a great pleasure for me today to introduce our JILA Visiting Fellow and speaker today, Joseph Thywissen. I just before I forget, reception is after the talk, it's not before. So please wait for that, and it's in the edge. It's in the edge wing, yes, in the X. It's in the H part, X wing, H part, yes. X. Okay, so let me start by saying that it's so nice to have Joseph here. I mean, he was a visiting fellow, and he splitted the visit exactly, and at the time of COVID, he could not come back, so that's why he's returning from to finish the visiting fellow. So the first part was in 2020. Yes, so it's great to have him here for 2 weeks. He is in X360. Joseph, actually, I was learning from Conrad today that Conrad knows him better than anyone here, that they attended undergrad programs and have been moved together. Then Joseph went to Harvard to work with Mara Prentice. I mean, Mara is a very important person for us, Gila, because she has helped us with the PFC for many years. And then Joseph went to did a postdoc in France, working with Alain Aspect and Philippe Bouillet. He was telling me that it's great that they were writing a report in honor of Alan recently, or just about the time of the Nobel Prize. And then he went to the University of Toronto, where has been doing fantastic physics. He's an experimentalist working with ultra cold atoms. He first started work with atoms in a chip. Then he had a quantum gas microscope, and he has been pushing for many years collisions with through P-wave interactions. I mean, people love S-wave collisions, but Joseph have done fantastic and beautiful work trying to manipulate P-wave interactions. So it's really great to have him here. He will be here for 2 weeks. So please go and drop by his office and talk to him. And well, let us give him the opportunity to tell us about the exciting ideas on orbital interactions between strongly confined fermions. This is for me, sorry.
Right. It's a pleasure and honor. Oh, it is on. Your waist. Let's see. Now there is. All right. It's a pleasure and an honor to give a visiting fellow talk here at JILA. As Ana Maria said, my last visit was the last 2 weeks of February in 2020. So you know why I didn't come back, and I'm happy to be able to. It's also a fun story to tell about P-wave interactions, and giving this talk at JILA is, of course, very appropriate because this line of research was really started through Debbie Jin's discovery of P-waves in potassium-40, and that's exactly the system we use in my lab, and that's no coincidence. We were following and continue to follow that path begun here. And so the story of P-waves, you'll see, is one of surprises, that we continue to think we're at the end of the story, and then something new comes along that's surprising. So let's see. So why do people care about P-waves? S-wave interactions are wonderful and are used all over the place in ultra-cold atoms. But there's a lot of desire to try to explore P-wave systems. And the three directions, you might say, that seem exciting are, one, to have topological superfluids, which can have interesting edge states and perhaps harbor protected quantum gates. With non-S-wave scattering, you break some kinds of invariants, and that shows up in transport signatures that have been predicted. And in few body physics, there are predicted but as yet unseen trimers and interesting few body states. All of these should come from P-wave systems. But when you look around at natural systems, it's still only helium-3 which is the uncontroversial P-wave superfluid. Even strontium ruthenate, which was for decades thought to be a P-wave electronic system, turns out to be S plus ID or something else more complicated, but not P-waves. So atoms, maybe they're going to be delivering on some of these promises. So what was seen here many years ago is that because of the centrifugal barrier for P-wave interacting atoms, which have one quantum of angular momentum when they collide, if you put a gas in a polarized state where fermions need to interact through P-waves, and you cool the system down below this barrier height, then the scattering cross-section is suppressed through this centrifugal barrier. But all is not lost. At low temperature, there is a Feshbach resonance, just like for S waves. And a Feshbach resonance occurs when the discrete bound state touches a continuum, and in a way that's coupled through hyperfine interactions, so that now the scattering phase of colliding atoms can be perturbed by coupling to this bound state. And so here you can see an enhancement in cross-section seen by Riegel and Jen in 2003. And then this was followed up by a study of P-waves at many institutions, both in theory and experiment. The problem is that, the problem is that associated with those nice enhanced elastic collisions, there's three-body loss. And so here's some measurements, for instance, of enhanced three-body loss versus magnetic fields around the same places. That's also seen in lithium-6, which has a P-wave resonance, that there's strong three-body loss. And this has continued to be studied in Mukiyama's group and a few others, where this loss is not only strong, but can be shown to be resonant. So is this the end of the story? It seems so. In 2007, I took a lovely hike yesterday and found this end of trail sign here. But you can see beyond the end of trail, Anna Maria's group is here in the tower and had some good ideas about how this might not be the end of the story for P-waves. And so I'm going to tell you about that today. I'm going to tell you about, first of all, how to think about orbital symmetry in the presence of confinement, an experiment where we take individual pairs and we put them in a deep optical lattice and study elastic collisions. And then I'm going to change gears and tell you about a different system where we look at the signatures of correlations between atoms in quasi-1D. OK, so the particles I'm going to tell you about today are all fermions. And fermions are those particles where if you exchange the position of any two particles, then you get the same many-body wave function back, but you need a minus sign out front. And so if I now just think about what two particles do, and I can write that wave function in terms of a relative wave function and a center of mass coordinate, the thing I care about is this relative wave function. And if it is an odd function of its relative coordinate, then when I exchange two particles, because I go x to minus x, I get that minus 1 required. So if I now show you relative wave functions, you're looking for relative wave functions that have this exchange antisymmetry if they're odd functions. So if I think about low energy scattering in free space, then I can write out this kind of relative wave function as a partial wave sum. And there the exchange of R1 and R2 is governed by the spherical harmonic. And this YLM has the property that if I take minus its argument, then I have minus 1 to the L, where L is the number of quanta of angular momenta. So for L equals 1, I satisfy this odd exchange parameter parity, and also for L equals 3 and anything odd, but not with L equals 0. And so for that reason, if I have fermions that are spin polarized, so all I have is the motion of wave function, then they need to be existing in these odd wave functions. And if I want them to interact, they'll need to interact with P waves. So P wave scattering can be parameterized a lot like S wave scattering. There is a scattering length with the units of volume. And if I get near a resonance, then it follows this kind of Fano form where it diverges as 1 over the distance from the resonance with a characteristic width. And that width is something like 20 Gauss in potassium-40. But there's also a subleading term, which is very different from S waves. So this subleading term, which is an effective range, can be neglected at very low energy for S waves because this K is up top here. But when the K is on the bottom, for dimensional reasons here, then as I get colder and colder, this term becomes more and more important, and I can't neglect it. So the complication of this kind of P wave, which is actually generic for all higher partial waves, is that you need to include these second terms. And so in the effective range, it's really a 2-parameter scattering phase. OK, so now that we switch gears a little bit and come back to this orbital symmetry question, but think about this with confinement. So imagine 2 particles, each held in the same harmonic oscillator, and they're allowed to interact. How do I then write down the fermionic symmetry of those 2 particles? So I have a harmonic oscillator for particle A and particle B with the same frequency and the same mass here. And I can write that in terms of raising and lowering operators in a quantized way like this. Now, because these 2 particles have the same mass and this is a harmonic oscillator, the magic is that I can rewrite all of this in terms of relative and center of mass coordinates. And now I have 2 different degrees of freedom. One is the center of mass, momentum, and coordinate, and the other is the center of mass, the relative momentum and the relative position. And I can still write that as a ladder of kind of raising and lowering operators, just like before, except now the center of mass and the relative coordinate have a different harmonic oscillator length by a factor of square root of 2, but the same frequency. And that's kind of surprising at first, that a ladder of states of relative degree of freedom doesn't get another square root of 2, but it doesn't. So the way I make these raising and lowering operators out of these is, if I want to add 1 quantum of relative motion, I have to have a superposition of an excitation for particle A and B with a minus sign. So that gives me a nice recipe. I can start with a ground state, and I can raise to have 1 quantum of relative motion. And if I rewrite that in terms of my original coordinates, it means either A is in the first excited or B is in the first excited state. And notice there's a minus sign between them. And that's what is required for this exchange antisymmetry. If I do it again, if I say, well, what if I have 2 quanta of relative motion in this confined system, then I get something more complicated. But notice that if I exchange the labels A and B, I don't get that minus sign anymore. Here, this is the same thing, and these 2 have a plus. So it's only with the odd numbers of relative motion that I can, again, have this exchange antisymmetry. And therefore, if I put 2 fermions in the same harmonic oscillator, I can only get the odd number of relative excitations if I'm following exchange antisymmetry. OK, so I'm going to represent that kind of relative motion now as this double-struck harmonic oscillator and assume that the center of mass is at rest. So I'm just going to tell you about relative degrees of freedom. So what I mean now is that what I previously called 0 center of mass, 1 relative, I'm just going to call the 1 state. It's the same state. So now you can see I've colored the antisymmetric states red here. And the same kind of thing follows through if I do this in x and y and z. So I go to 3 dimensions, and I now have, again, relative and center mass coordinates. It gets a little more complicated. The eigenstates for the non-interacting 3D harmonic oscillator should have in x, in y, and z. Or you can write them out in a kind of hydrogen-like way with an NLM, with a principal quantum number, an angular momentum quantum number, and a projection of angular momentum. And for the odd systems, where L is equal to 1, then again, the total number of excitations, which we'll call n relative, can be 1 or 3 or 5, et cetera. So this means that if I put 2 fermions in a harmonic oscillator, this is the lowest energy state that they can be in. And then I could go up to the next vibrational state, but is 2 h bar omega away. Any questions about that? Okay.
How do they interact with each other, like external potential?
Yes, great, good question. So I didn't talk about this yet. So far I've just talked about a non-interacting problem. And if I want to have an interaction potential, that interaction potential is usually only dependent on the relative coordinate. And so again, it'll appear in this relative coordinate space, not in the center of mass coordinate space. So now this is the thing we'll have to turn into, for instance, a p-wave interaction potential. Yeah. Okay, so and when we do that, then I'm not going to have these non-interacting eigenstate energies. I'll have a slightly higher or lower energy if I have an attractive or repulsive interaction. Okay, so now the experiment that we've done recently is to load these atoms first into a 3D optical lattice and do that in a low energy regime with spinful atoms so that all the multiple excitations are gapped out in higher orbitals at first. And so we load this lattice, and there are different kinds of things you find on lattice sites. Sometimes you find these pairs that we're interested in studying. Sometimes there's a spin-up and a spin-down atom. And sometimes there's just single atoms on some lattice sites. And so what we're going to do is study now the energy of these different possible combinations. And the lattice has turned up to be a very deep lattice. And that's useful because you can think of each of these sites now as one 3D harmonic oscillator, which is isolated from all its neighbors. And at first, if you're thinking the problem was high density of atoms and 3-body loss, it seems like a terrible idea. If I calculate the average density and then I use a 3-body loss coefficient, then you would think these atoms live for nanoseconds. But that's the wrong thing to do because we load this in a condition where 3 particles can't be on a single site, energetically selected through a loading procedure. And now when we turn up interactions, there isn't a third particle to have that 3-body interaction. So it's a nice kind of petri dish for pairs of atoms. Okay, so the principal experiment in that lattice is now to measure the strength of p-wave interactions. And so we start with them in their lowest state, which don't have a p-wave resonance. And then we do a RF spin flip into an interacting state. So potassium-40 in its lowest state, which I'm going to call spin down, is 9/2 minus 9/2, and then we flip to the 9/2 minus 7/2 state. And what we're doing in spectroscopy now is measuring the difference in energy between atoms that are near a Feshbach resonance and atoms that have only the background scattering length. And what we see is a spectrum that looks like this, where as a function of the frequency of this RF spin flip, we see a peak where we're flipping single atoms from spin down to spin up, and then a peak at higher energy where we flip a pair of spin down to a pair of spin up, or also one at lower energy, pair down to pair up. And so it's a complicated structure because it's multi-branched. At any one magnetic field, we see that when we're starting from this n equals 1 ground state, we can either go to an upper branch, which we're calling branch 1 here, or a lower branch calling branch 0. So, so this is one magnetic field, and I'm just scanning the energy of RF spin flips, allowing us to go to one or the other of these states. If I now change the magnetic field and repeat the spectroscopy, then for a given magnetic field, I see a couple of peaks. I'm just denoting here now the peak location in interaction energy. And we see this is a complicated structure where we not only have a multi-branch structure go either attractive or repulsive interactions, but even on the repulsive side, there are multiple peaks we find. That's because p waves can have multiple projections. So with L equals 1, you can have ML equal -1, 0, or +1. And they're split by a dipole-dipole interaction so that these occur in free space at about half a Gauss separation. When we load things into the lattice, it's still about half a Gauss between, let's say, this peak and this one. But now at one field, we get to see multiple different interaction energies.
Sorry, what is this out? Sorry.
Okay, yeah, please. Please interrupt me.
I just wondered,
Yeah.
are there any axes you define the motional state quantization?
Yes. So in this lattice, there's a magnetic field which is aligned with one of the directions of the lattice. And that's what I'm always calling the z direction here. And then that also distinguishes whether you have that m equals 0 orbital, which is, let's see, m equals 0 is a dumbbell that's aligned along z. And then you can have ml equals plus minus 1, or you can call that x plus iy or x minus iy.
And microwave is also.
It is, well, it is not aligned with z, otherwise we couldn't spin flip. So it has to have some projection perpendicular because it's the oscillating transverse component of the field which will change ML. Yeah, great questions. Okay, so now we can repeat all this not only versus magnetic field, but again at a deeper lattice, which makes a stronger on-site harmonic oscillator. And you can see that this kind of resonance type shape here is shifted to higher magnetic field. So at a stronger field, there's a magnetic, at a stronger confinement, the Feshbach resonance moves to higher field. All of this sounds complicated. Luckily, there's already some prior theory about solving this problem of two interacting atoms in a harmonic oscillator, and then adapting that to the anisotropic scattering volume is something that Anna Maria and her group did. So we find a beautiful collapse if we just rescale everything I've shown you in terms of the harmonic oscillator parameters. So we scale that scattering volume by the harmonic oscillator length cubed, and we scale the energies by h bar omega. And so now at different on-site oscillation frequencies and also for the different ML projections, we see our data collapse onto this kind of dispersion curve. So here you see quite clearly there's a lower branch and there's an upper branch. And now the theoretical lines here are a pseudopotential theory, which I'll talk a little more about. And you can see that the energy shift goes to a full h bar omega here and almost to a full h bar omega here. And these two shifts, when you're halfway between two allowed free non-interacting oscillator states, is the maximum shift you could have. After that, it becomes non-interacting in the asymptote. And so that's the unitary point. It's also where the scattering volume diverges. And it's exciting to see this because we couldn't see this in the presence of three-body interaction. It was just too many losses. So it's also a way we can test simple theories about now how to describe interacting pairs of atoms. And so this pseudopotential theory uses this kind of interaction potential. So the V and that two-body harmonic oscillator potential I showed you earlier, Hamiltonian earlier, is this. This looks really complicated. It has some crazy derivatives in here. And it also has a prefactor which is scaling with a scattering volume. And I've just told you that in our data, this prefactor diverges at one point. And yet the theory lines are continuous across the data. The reason is because once this parameter diverges, it enforces a boundary condition where the rest of this goes to 0. So the pseudopotential is just formed in order to meet the short-range boundary condition for all scattering volumes. And again, now let me show you not only the pseudopotential theory, but a much more sophisticated theory done by Jose and Cao, which includes coupled channels calculations and a full molecular channel. And there you see that the wave function predicted by the coupled channels calculation agrees really wonderfully with the pseudopotential calculation at long range. But we're cheating just a little bit. And the reason is because at short range, the pseudopotential does diverge. And so you have to cut off this normalization at one point. And the normalization cutoff of about 50 Bohr ends up making all of this work very nicely. So you see how we go now from a non-interacting or nearly non-interacting wave function to a unitary point, and then, at least in theory, can go back to a non-interacting point with two more quanta of relative motion. Yeah?
I sort of have a trivial question.
Yeah.
Just my computer probably. So n relative is 1, that first asymptote.
Yeah.
And then why is there 5 halves on the left?
Because there is, so the energy is would be 3 halves if it were 3 particles in the ground state, but you can't have 3 particles in the ground state because, 3 degrees of freedom in the ground state, because you need 1 quantum of orbital angular momentum, so I need to add another h bar omega. So 5 halves h bar omega is the lowest energy you can have for 2 fermions in 3D in the relative coordinate. Yeah, great question. Okay, so I've told you about how these isolated pairs in a deep lattice can now give us confidence that we really understand, even for strongly interacting atoms, how to describe P waves using pseudopotential and how to think about symmetry. Now let me switch gears and tell you an experiment where we look at quasi-1D. And underlying quasi-1D and all the calculations is again use of the pseudopotential, which we now have a lot of confidence in. The experimental signature is not going to be spectroscopy anymore, not measuring energetic shifts, but instead measuring the probability of finding 2 particles close to one another. So this 2-particle correlator is something sometimes called the contact. And let me describe what that is. If I take 2 particles at very low energy, then I know what they're going to look like when, especially if I talk to people like Jose who can do a couple channels calculation, I can calculate the wave function of 2 particles when they're very close to each other. And when they move far apart from each other, then things get very simple because they're non-interacting. But now for a mini-body system, all the interesting physics is in this long-range, low-energy degrees of freedom. And this is a non-trivial problem. So mini-body physics can't be solved even by strong computers for fermions that are interacting. But if all of the many-body physics is at a low energy scale, and I again think about what happens when any 2 particles come close to each other, that's happening at a very high energy scale and short length scale. And so the 2-body density matrix, which traces out 3 to n particles, has a known shape at short range, just given by 2-body physics. So if that's the case, which requires a real separation of energy and length scale between the range of the interaction and the typical interparticle spacing, and that we have in dilute gases, then I can connect these two by saying, okay, the many-body physics is just a source of particles colliding, and the number I find at short range is a function of what's happening in this mini-body. But the shape here is known by 2-body physics. And so this nice combination of ideas, knowing that the wave function, everything but the norm of the wave function is known at short range in ultra-cold dilute systems, allows us to define a parameter which is just the strength of this short-range correlator. And that's what I'm going to call the contact parameter. So the contact is a quantity which has really come into people's attention in this century. It sounds very simple as an idea, and I don't really think there's anything about it that requires very modern physics. But no one really thought about this parameter until ultra-cold atoms came around. And then all of these people, including Klaus Moldler, who's here in the audience, explained to us how there are certain relations, universal relations, that connect microscopic properties, such as the correlator I've been talking about, to macroscopic properties, such as thermodynamic relations, virial relations, equations of state, and things like that. And appearing in every one of these either micro or macro relations, there's this C, which is the amplitude of that short-range correlation. So these contact relations were understood in between, say, 2005 and 2012 or so for S-wave interactions. And one of the surprises in our path for P waves is that we found that they also follow a set of contact relations. And this is a story, by the way, I like to tell because it's all about graduate students driving the science. I went down to the lab. We were studying some S-wave physics, and my graduate student was running the experiment for the first time on his own because the senior graduate student had gone on vacation. And I said, Scott, how are things going? And he says, terrible. When I'm supposed to see a signal, I don't. And when I'm not supposed to see a signal, I do. And what he was seeing is that when fermions are near a P-wave interaction, they didn't need to decohere in order to be correlated strongly. And so he was seeing a P-wave correlation exist at very short times in our mixtures. When you're near that P-wave resonance, atoms, because of three-body loss, go away. And that's why the senior graduate student knew, because he had read the papers of Debris Jen and others, to skip that range of magnetic fields, because bad stuff happens there. But so by ignoring the advice of old people, Scott discovered that P-wave correlations are very strong, and we realized that they also obey a really nice set of contact relations where, for instance, there is a two-body density matrix which has a well-known form and this kind of scaling regime, and we can relate that to adiabatic relations and momentum relations, and all of that can be measured in our lab through RF spectroscopy. So what's really neat is that we can look at spin flip rates with RF spectroscopy and know something about two-body correlations. And in so doing, we measure these contact relations. OK, so that's the observable that we are going to measure. But now we're going to measure them in one-dimensional ensembles with P-wave interactions. So far, I've told you really about 3D interactions. And how do I trace that down to 1D? Well, in 3D, there's L equals 0, S waves, L equals 1, P waves, D waves, et cetera. The same is true for 2D, except in 2D, if I have a P wave, it can only have a plus and a minus projection. Same for a D wave. It can only have a plus and a minus ML projection. You're either clockwise or counterclockwise if you're in 2D. And in 1D, you can't have anything that's beyond the first two. And the reason is because a wave function is either odd under particle exchange or even, and that's it. There's no other partial wave equivalent. So once I measure the S wave stuff in 1D and the P wave stuff, I'm done. There's no other partial wave to talk about. But people haven't really measured this very much. So we set out to do that, thinking we would know what we're going to find. So we strongly confine in two directions. And this is kind of like the lattice I showed you earlier, but one of the directions has been turned off. Okay, so we're strongly confined in two directions and weakly confined in a third direction. And the ratio of these is something like 10 to the 3, so 1,000 to 1 aspect ratio. And there are about 30 atoms in each of these 1D tubes. So what do we see? Well, if I don't have a lattice on, and I look at this correlation strength I just mentioned to you, the contact parameter, then there's a peak around the ML equal plus minus 1, and there's a peak around the ML equals 0, and those are about half a Gauss apart. If I turn on one optical lattice, then I make pancakes, and so I can suppress the X collisions, because you can't move continuously and perpendicular to a strong lattice. But I still have two peaks. If I now have lattice on along the magnetic field, I can get rid of this Z peak and still have motion in the XY plane. And so I still have these kind of correlations. And this has been seen, for instance, in Zurich and other places. And now if I turn both of those on, I should have quasi-1D systems. And you might expect I just have the Y left over here. And we see this. Okay, so This is some very old data. We have a lot nicer data, but I'm showing this because I've been shopping this around for years. We kind of saw this in the lab, didn't really know what it was. And it took us a long time to figure out what was happening here. So why is it that when you turn on both of these, you don't just have this one peak left, but you have this huge, broad resonance? And I was excited at first because I thought this was maybe some signature of broad S-wave-like physics in 1D, and there's some reasons to think that might be what's happening, but it's more complicated than that. So what are we doing in these kind of plots? Well, our procedure is that we load atoms into these lattices, and then we look carefully at what kind of excitations are left over with a little bit of orbital excitation. So what is the excited transverse population left over? And we measure that by doing something called band mapping, where we turn off the lattice quickly on the time scale of scattering, but slowly on the time scale of the band gaps in the lattice. And so you can see discrete population boxes that correspond to ground state and first excited state in these transverse directions. And if there's too much here, we know how to clean them out. We can do some amplitude modulation, which reduces the population here. You can see that there wasn't a lot to start with, but OK. Once we've cleaned out the population in these higher bands, then we do spectroscopy. And as I've already mentioned to you, there's a certain RF spectroscopy scheme which measures these contact parameters. OK, so what do we find? First of all, as the characteristic signature of a contact is that when we detune far from the single spin flip, there's a polynomial decay here, 1 over frequency to the 3 has power. And that scaling law is the kind of smoking gun of odd wave interactions, in this case in 1D. And those odd wave interactions also tell us that the momentum distribution has a 1 over k squared tail at high momentum due to interactions. So we can now change confinement strength and change the magnetic field and see if we understand what the odd wave scattering is doing. And we see something like this, where for various different lattice depths, the correlation strength versus magnetic field, but now magnetic field written in terms of an odd wave scattering length, look like this. If I don't rescale things, it's a mess. But once rescaled, we see that correlations do increase as we head towards a Feshbach resonance. But when we get near the Feshbach resonance, these 3-body loss mechanisms take over again. And this prevents us, just like in 3D, from seeing unitary interactions. So the contact we see is at most something like 2 times 10 to the minus 2 of what you would have expected for a unitary gas. I've written this in a kind of dimensionless form. And you see it does that for moderate or strong lattice depths. And so it's a little disappointing, because we go and look at these odd wave interactions, but the same story is there. I mean, it's nice to see odd wave interactions. One nice thing is that this is certainly a 1D system, because we can show this data collapse by scaling versus a new scattering length, which is more or less the old 3D scattering length, again multiplied by a harmonic oscillator parameter. There's still an effective range around, which is important. And then there's this regime here, which is strong atom loss. And the strong atom loss was studied by Randy Hewlett and by Ken O'Hara in lithium. We see a kind of similar thing. And then there's this. And you may be looking at this and saying, oh, you had a theory, but it doesn't seem like your theory really agrees for weaker interactions. So what is this spurious signal? Well, the spurious signal is actually the interesting thing, it turns out.
Can I ask you? So
Yeah.
this scattering volume that you get is similar to I mean, we have 2 scattering volumes. So is the m equal to 0, m equal to plus 1?
In this case, there's only 1, because I only have y collisions in y. And so
But if you think as a 3D collision, I mean, maybe I'm
Mhm.
I mean, it's really, really then, because typically you think that the collision can be of 3D-ish.
Mhm.
So this
It is.
picture
No, it's still the case that the 3D effective range is small compared to the confinement length. So at short range, the collisions look 3D.
Okay.
They're just connected to asymptotic degrees of freedom that are 1D. So you can think of it as a kind of boundary matching condition of how the 1D collisions feed a 3D interaction.
I see.
Okay, so what is the spurious signal? The spurious signal is actually a very strong signal if we don't do this band cleaning, but instead drive population into that first excited band. And so here, this might not look like a lot of population in the first excited band, but look how strong the correlations are. So there's a regime in which we see the correlations where we expect them for odd wave interactions in 1D, and then there's a tremendous regime in which we see what we don't expect. And this is once again this mystery of the wide Feshbach resonance that I mentioned earlier, that across a very large range of magnetic fields, larger than you would have expected, you see strong correlations. So it turns out that these correlations are explained by even wave collisions along 1D. And the way you can get even wave collisions is that if I have an atom in the first excited band and I have an atom in the ground band and then they collide, the wave function now has a component along the weak direction, but also I need to think about what the wave function is along the strongly confined directions. And there is a state which has one quantum of excitation shared antisymmetrically between the two atoms in the same way I showed you at the beginning of the talk. That's a singlet-like wave function. I had written that as a 1, 0, 0, 1 back then. Here I'm changing notation. I'm calling the n equals 1 ground now. I mean, n equals 1 excited, n equals 0 ground. But it's the same wave function here. You have this antisymmetric entangled wave function where two particles are sharing this one quantum of transverse excitation. And therefore, the total wave function can have that exchange antisymmetric part in the transverse direction, but an exchange symmetric part along the weak 1D direction. And so that's how you get even wave collisions along the 1D direction when you populated these orbital degrees of freedom. In other words, if I wrote now the relative wave function of the transverse directions, then I would have something with a node in it that's an odd, either an x for one of these modes or y or z in the other direction. Okay, so because this is confined in two directions, now there's a harmonic oscillator in the x or in the z direction, so there's two kinds of ways you can have an orbital excitation, and those continua are split. So there's the ground band where you can only have odd wave interactions, but then if I have an extra h bar omega of a pairwise excitation, then I can have either x or z, and then those two can be split if the confinement is anisotropic, because I have independent control of those two lattices. In addition to that, I need to be keeping track of which of these is the ml equals plus minus 1 and which one is the ml equals 0. And that gives me an additional dipole-dipole splitting, which moves these peaks further apart. OK, so now as a function of magnetic fields, I'm not seeing one big broadened peak, but underneath that, there should be 3 different peaks. And indeed, if you look carefully in this data, you see that there's this expected odd wave plus these 2 even wave peaks, which blur into each other at high confinement strength, but actually are distinct correlation peaks at lower confinement. So the smoking gun of this signature is that I go back now and I measure the contact relation with RF spectroscopy and find not the odd wave, but the even wave correlation. So the power law of this transfer, here I'm showing you on a log-log plot, is in omega to the minus 5 halves, which tells us the momentum distribution looks like 1 over k to the 4th. And that's very much like S-wave interactions would give you in 1D. Whereas when I did all this for odd waves, I showed you an omega to the minus 5 halves, which was 1 over k squared. So this is showing you that emerging from these p-wave interactions and orbital degrees of freedom, we have an emergent S-wave interaction in this quasi-1D system. There's also an interesting singularity that exists, that if I can scatter with p waves, and I have this orbital degree of freedom, I can kick now to the n relative equals 3, which is a band at 2 omega away. And so there's a way I can use RF to couple to another wave function. And that is another thing you don't see for the odd wave, for the ground states. All right, so now we can measure a contact parameter, and we can now look at this even wave contact parameter in quasi-1D. And the story is now a bit different from before, because as I move towards the Feshbach resonance, I still do see losses, but by the time the losses take over, the correlations are near unitary. They're almost as strong as you could expect them to be. And so here I'm showing you again a dimensionless contact parameter, which is roughly 1 at unitarity, and you see we're a good way there. You see a similar kind of behavior at 2 different confinement strengths. Those numbers are the same. One of those is supposed to be 80. And this here is a theory with no adjustable parameters, but a range of measured temperatures. OK, so let me see. Once again, there is a new 1D scattering length, which is the old scattering volume, but now rescaled by a harmonic oscillator length. And that indeed controls the correlation strength. Let's see. OK, so why is there a much stronger contact parameter? The reason is because p-wave interactions have a coupling which is stronger when the momentum of the collision is higher. And so this quasi-one-dimensional gas has a Fermi energy which is much lower than the excitation gap to the transverse directions. That's why we call it 1D, that all the interactions along the tube are low compared to the energy scales of quantization in the transverse direction. But now these new kind of wave functions, which have an orbital excitation in the transverse direction, have the full energy of that gap, and therefore the momentum associated with it. So they have really strong p-wave interactions that come from this orbital, this high energy orbital interaction. And that's why the underlying interaction energy is now strong, and you can shift the interaction energy of the gas a good fraction of the Fermi energy. There's one more nice thing about these emergent S waves, is that they might be scale invariant. So if I look at the scattering amplitude or the scattering phase for S waves, just as I mentioned earlier, the effective range term goes away at low energy. So both in 3D and in 1D, as I get colder and colder, here I'm showing energy of collision in a theory plot, and now I scan magnetic field, the range where there's a strong scattering amplitude near unitary gets broader and broader for lower and lower energy collisions. And that's like S waves do. Whereas for odd wave scattering, as I get lower and lower in energy, there is still a unitary point, but it's very narrow magnetically, and it's also narrow energetically as I get all the way to the resonance. So because we have an emergent S-wave scattering, it follows this form, and it means that already for the typical energy scales of our experiment, which are something like 10 kilohertz, we can pretty much neglect this second term and understand our 1D S waves, emergent S waves, in terms of a single scattering parameter. So that's what I want to tell you today. I told you that in 3D, we can see a ladder of on-site interaction energies due to p-wave interactions. we can tune that all the way up to an elastic unitary point. And the lattice allows us to suppress three-body relaxation. And I didn't show you data, but we can also extend the dimer lifetime by moving away from the resonance. So an interesting prospect now is to lower the lattice depth and allow atoms to interact with each other. Now, you might seem like a bad idea, since we did all this to suppress three-body relaxation, but maybe there's a Goldilocks regime in which there can still be super exchange, virtual excitations that don't have three-body, on-site three-particle populations. Already Anna Maria and Mikhail and others have done some nice calculations on that. More generally, let me just say that S-wave physics with spinful systems has dominated ultra-cold Fermi gases, and this work shows that there's some life in also employing orbital degrees of freedom. The second part of the talk, I told you that we made both odd wave and emergent even wave gases. For the odd waves, we could compare to some nice high temperature theory with no adjustable parameters and see that they agreed for moderate correlation strengths. But near resonance, we saw that we could get nowhere near unitarity, orders of magnitude away, because of three-body loss. On the other hand, in that same regime of magnetic fields, we can see emergent S waves that do have strong near unitary correlations. And there's some suspicion that we haven't demonstrated, but just at least in theory, this should be energetically broad at low energy, which is nice because maybe there could be universal mini-body physics in that same broad resonance. So it seems that the mystery of the White-Feshbach resonance is solved. This massive peak here actually had several peaks underneath it, and orbital degrees of freedom were coming into play. And I'm looking forward to the next twist in our path to study P-wave physics. Let me just say that I had a great team working in the lab, and many of these ideas were developed in collaboration with people here at JILA and also at HKU, Shizhong Zhang and Jeff Maki. Thanks for your attention.
Thank you, Joseph, for the great talk. I think we are open for questions. Hello.
Yeah, really nice talk. I guess I just wanted to ask about the first part, where you have a strongly confined 3D lattice.
Mm-hmm.
So can you control the filling? That's the first question. And the other is, can you then head towards a direction where the hopping between sites becomes substantial, so then you can look for sort of three-dimensional superfluidity, paired superfluidity?
Yeah. We've been reading your paper on some of these prospects. Indeed, your question about filling is exactly the experimental challenge for the next step. So what we'd like to have is two doubly occupied sites next door to each other, and then see whether those pairs can now interact. And in order to do that, we need to be in a very low entropy state. So we need to be in the second band insulating state. And as of last year, we weren't there in the experiment, but recently we've worked hard and can make now gases at something like 0.06 TF. So we're really excited about that, and we're going to try to load the lattice again and see if we can see band insulating signatures. So if we can see nice band insulators, then we'll tune to interaction and look for these super exchange signatures, which might have some promise. Now, another approach, which you're mentioning, is what if you just go to a n=1 band insulator and allow tunneling, or especially dilute filling? Maybe there's next nearest neighbor interactions or other types of interactions. And I haven't thought clearly about how cold we need to be to get there, but my sense is that the critical temperature for superfluidity is very low. And so it's going to be, yet again, temperature limited experimentally, I think.
But what have you learned about three-body in that limit when you begin to allow hopping across? Is that kind of come back and haunt you again?
Yes, it'll be very much be what we're looking at. We're hoping for kind of a xeno suppression of those lossy mechanisms, because if they're extremely fast, they can maybe suppress themselves.
Okay, thank you.
Yeah, we don't have a magic bullet yet, though.
Yeah. No, but they can manipulate the lattice geometry to
Yes,
make it
that's right.
energetically unfavorable. So.
Yeah, great.
So you said for previous P-wave Feshbach experiment done in JILA was not so clear because of the three-body loss, but if we isolate two atoms in lattice, did someone see like clear spectrum what you saw in this different method?
No one had really looked at this in a lattice before.
Okay.
Yeah.
I see. So
It was just
nobody tried.
It's not that someone tried and didn't succeed previously. No one had tried, so far as I know.
So yes. So you think if we separate two atoms, even with previous method, we could see this kind of clear
I'm not
spectrum?
sure quite what you mean by previous method.
Previous the Feshbach resonance sweeping.
Oh, okay. Yeah, maybe. One thing to say is that you need to, and I didn't speak much about this. We're using Raman transitions to populate the first motional band.
Yeah.
And arranging things so those transitions are spectroscopic and non-destructive and well controlled, et cetera, took us a little while. So I think, for instance, we do RF spectroscopy here, even though we have spin selective Raman transitions, and there's some experimental subtlety behind why we just didn't do Raman spectroscopy, and it's because those transitions are broad. So I think there is a toolbox we assembled in order to do orbital physics in the lattice with P waves, and some of those tools just hadn't been developed previously.
I see it. Thank
you. Any more questions? Maybe I ask one quick question. So, for the 1D event S-wave or emergent S-wave interactions, do you see any suppression of three-body losses?
No, it still seems pretty lossy. I mean, you would hope that if this is like an emergent S wave, and now there's a pseudo spin again, where you need to have, an orbital excitation, that a third particle can't do the same thing. And so just like this kind of lovely suppression of three-body loss for spin-full systems, we haven't seen evidence of that yet. I still kind of think this should happen, but it's not as if the losses went away.
Okay, I see.
So I'd say we probably haven't. I couldn't tell you they're not, say, 10% lower. We haven't really quantitatively studied them, but they're not orders of magnitude lower in raw rates. On the other hand, because the system has orders of magnitude stronger correlations, maybe the time scale of the dynamical, the elastic physics time scales have been boosted, and the three-body scales are just comparable. That's already a kind of relative, suppression. Yeah.
Great.
Yeah. Good question.
Excellent. More questions?
Looks like your in your 1D experiment, X and Z degree of freedom just works like an internal state.
Yeah,
of the atoms.
you can think about it that way.
Yeah.
Except there is an n equals 3. In other words, it's when you think about the interaction, you start with this n relative equals 1, but as you're increasing the interaction strength, you're mixing in n relative equals 3 states. And there's no analog of that for spin-full systems that I need to include an infinite ladder of spins in order to just describe interactions. But at, let's say, weak interaction strengths, you can kind of think about this as a pseudo spin, which is, I think, what you're saying, right?
Yeah. Then can you expect some super exchange on that degree of freedom if you make them degenerate?
Oh.
like, and then crank up the lattice, and then.
Oh, so you're saying, you're talking about
X
both
and Z.
two different flavors of S waves,
Yep.
and now flip between them.
That's what we.
Oh, okay.
Yeah. I mean, two different orbitals.
Oh wait, are you talking about the quasi-1D system?
Yeah, sorry, quasi-1D system. X and Z might be like
And you're saying exchange between sites, or you're saying you're saying?
orbitals.
Yeah. So I think it's a little different than what.
Okay, it says, but in a generalization of that, I mean, you need two different, yes, you need singlet and something else. So you need singlet and triplet. We can talk, but that's what we did, yes, singlet
Yeah.
and
Oh,
triplet
okay.
in not only one orbital, but two orbitals.
Yeah, I mean, the orbital, since there's two different orbitals that are emergent S, you could now imagine a superposition of them, and that superposition can have a phase, and so there's actually kind of like two
Like
flavors of,
CDX.
yeah, yeah. There could be something fun to do there. What would you suggest, actually?
I was just curious if
It's a
this is
nice degree of
possible,
freedom,
or
but,
like it's just like doing like I don't know, antiferromagnetic physics with like orbital angle, orbital degree of freedom.
in the 1D system.
Maybe you can extend. Just
I think you need higher, but we can, I think you need another degree of freedom. But we can talk, I mean,
Yeah.
yeah, we like to talk more. Okay, so I think we are, I mean, we need to go and have cake, so we are delaying so much the cake, so please join us to
Thank you.
thank Joseph.